Today, my name's Damien. I'll be going through a presentation on heat transfer and simulation. We're going to be talking about both using SolidWorks Simulation Professional and SolidWorks Flow Simulation, both capable of doing heat transfer problems. So a quick overview of what we're going to cover today. Quickly, we're going to talk about why we should use simulation, an overview of some of the different types of heat transfer that we get, and then we're going to move into some case studies. So we're going to look at a LED light, and we're going to use SimPro to analyze the heat distribution through the heat sources, the LEDs, through the circuit board and the heat sink at the back. Going to look at a second quick case study of how we can use those heats to look at thermal expansion. So we're going to do a structural displacement analysis on some bellows. Then we're going to talk a little bit about the difference between steady state transient studies and take a look at an example, a transient study. I'm going to hopefully just review some of the common pitfalls for these types of studies in SimPro and introduce flow simulation and how that can work. I'll probably do a flow sim on the same model, and then I have a fourth example of a heat exchanger. We're not going to set it up, but we're going to review the results in there and how it goes through, and a quick review of some of the other types of studies that we might be able to perform in flow sim. And there'll be time for any questions, and then we'll review. So moving forward, why would we want to use any simulation product? So there's a couple of things to review and talk about. When we have designs, be complex or simple, it can give us the tools to figure out how we can meet particular design criteria and enhance the functional performance of that product, get heat away quicker or reduce the amount of displacement, and help us meet regulations so things don't overheat or don't break or they last a set length of time. Because we're doing this, it allows us to reduce the amount of redesigning when things go wrong. If we do a physical prototype, then we can make sure that we know when we come to actually test that we've done it right in the first place by virtually prototyping in the first place. So we can do things like weight, shape optimization ahead of that physical simulation. Allows us to detect any problems early in that design process. So as a designer, it allows us to have insight into the decisions we're making at a time and look at alternative designs virtually that might be slow or expensive in the physical world. In the case of flow simulation, it actually allows us to see how air and fluid might move that would be difficult to do in a test environment. We can actually see more in a virtual study than we can in a physical test. So, and ultimately, can allow us to create better quality products, make them more efficient, reliable. So the SolidWorks proposal, a traditional serial process, talks about doing a preliminary project, doing your detailed design. Once that's finished, physical prototyping and testing or validation, and creating the technical documentation would be proceeded. At any point, if there's an issue, we'd have to go back through that detailed design stage. So the SolidWorks proposal is that we can do those concurrently and thus reduce the development time. And today we're going to look at one of the aspects, design validation. Obviously, technical communication can be done concurrently too. So types of heat transfer. The three types, predominant types, are conduction. So when objects are touching each other, they can conduct heat through them. And radiation allows heat to transfer through either air or a vacuum through electromagnetic waves. So these two first are the types we're going to deal with in our simulation professional. And just out of interest, radiation is really about hot bodies. So if we have very hot bodies or a big difference between heat between bodies, radiation will form a bigger part. Typically though, convection is one of our most common forms of heat transfer, where air is heated up against the surface of a warm or hot body and it moves away and takes the heat with it. And we can model this in FlowSim, but not in Simulation Professional, where we have to specify it as a coefficient and understand what it is. So just a little couple of charts to give you a feel for dealing with conduction in solids. The thermal conductivity constants are quite varying, as you can see, for insulators right down at 0.1 or less, all the way up to pure metals at 100 plus, which is a factor of 1,000 different between an insulator and a pure metal. So the choice of your material for your model is very important to make sure you're modeling what it is you're looking at. So looking firstly at conduction. So when we create a SolidWorks model and we touch two objects together, as we can see in this first screen here, they are perfectly touching, and our equation for conduction is held through, and the heat will perfectly conduct based on the temperature differences between them. However, in reality, we often will have air gaps, okay, and the flow of heat through the air gaps will be significantly less than that of the areas that are touching. So those air gaps and roughness and the amount of contact pressure between the two faces can all affect the conductivity between the two touching faces. So this thermal conductivity is sometimes expressed as a thermal resistance, which is the inverse of conductivity. So rather than conductivity being watts per degrees C, we can have degrees C per watt. So we can see some typical examples here. A dry joint in an electrical component will have quite a high thermal resistance, whereas when we apply thermal grease, fills in many of those air gaps and creates quite a low thermal resistance value. So some different examples. So when we create our model, we can specify the thermal resistance between those faces. So as we've alluded to already, there are some of the differences between running heat transfer in Simulation Professional and SolidWorks Flow Simulation. We can see in Sim Professional we use the finite element method, and allows us to have good accurate conduction models and good accurate radiation models. However, when heat is transferred through convection, so for example in this forced fan case, the air will flow out, we need to tell the faces of our solid the coefficient of convection. Okay, so this is a value we have to specify, so we have to understand what it is to get an accurate answer. So it's estimated based on our judgment. However, the other alternative using flow simulation, the CFD model, SolidWorks FlowSim uses the finite volume method, which allows us to do, again, accurate conduction models, accurate radiation models. And for those of you involved in the HVAC industry, there is advanced radiation models that allow different amount of radiation absorption through glass and other objects. However, what it can also do is model the actual airflow and provide those coefficients of convection as an output. Not that we need them, but they could be used later if we chose to. So we don't need to understand the convection model, we just understand the material and the gases, and we get a more accurate convection model. So before we do a case study, just a few examples of heat transfer coefficients for convection. We can see these also can vary wildly. So just a natural convection, like an object, a warm or hot object in air, could be somewhere between 5 and 25 watts per meter squared Kelvin. all the way up to condensing steam, could be 6,000 to 120,000 watts per meter squared Kelvin. Very efficient transfer of heat with the condensing steam. So again, understanding the model is very important. So clearly, if we have good airflow through a heat sink and a fin, the heat transfer coefficient will be higher than the one that has restrictive airflow. Okay, so let's look at our first case study, and I've got a typo I forgot to take out. So we're going to look at an LED light simulation in Simulation Professional. Before we do that, we just want to take one little PowerPoint. For those of you that have already done structural analysis, there are some nice analogies that help us understand how to set up our thermal study. So when we're talking about displacements as an output in a structural analysis, that has an analogy with temperature. As does stress have an analogy with heat flux, which is our movement of heat through our structure. And a load would be similar to having a heat source or a heat sink, so either heat into the model or heat out. And one more thing that's not on there would be contact, which is equivalent to conductivity or thermal resistance, thermal conductivity or thermal resistance. Okay, so here we have an example of a nice light bulb. In this model, I've got a simplification that takes away the housing just to make the study run a little bit, have a little less setup. So we can see in here we have some series of fins. We have an aluminium plate. It's currently hidden, which I am going to just find and show. Give me 1 second. My bad, I should have shown it ahead of time, and a PCB board. Luckily for us, when we're working with SolidWorks models, many of the tools for SolidWorks are also available for doing simulation studies. So for example, I can utilize a exploded view, okay, and we can work with this to help us set up and activate and control components very easily. Okay, so the first thing we're going to take a look at is building a thermal study. We're going to make a new study just using our simulation add-in. And we're going to take the second type, which is going to be our thermal study. Webinar, study 1. Okay, so we're just going to make this and go ahead and start building my geometry together. So we can see in my tree, I have already specified my heat sinks have been specified as copper because they have been pulled from my SolidWorks model. So if we have our SolidWorks material set up ahead of time, it can save us a lot of time to define them. Otherwise, we'll need to go into each individual item and specify, for example, an aluminium for my plate, and keep going through everything else that I need. Apologies for that. And the second item that we're going to look at is going to be the PCB board. Okay. So applying a material to a PCB board, we can utilize something called an orthotropic material. So I have one that's been done before, PCB, in here. We can make our own materials. Some of the differences between isotropic and orthotropic is that isotropic means it has values equal in all directions, whereas an orthotropic material will have different values for strength, yield, coefficients such as thermal conductivity in X, Y, and Z. So in the case of a circuit board, it will conduct a weld through its plane, but not through its thickness. So we can see Z is showing us the thermal conductivity through the thickness. All we need to do is choose a reference piece of geometry, such as a top plane. to apply it appropriately. Okay. So lastly, we can see all of our LEDs. We've modeled these like little chips with a junction and a case. Okay, but we could have done them single bodies. We did it this way just for the flow model later, just so we can see some of the extra things that are added in here. These parts here, we can select them I think it's all these ones here. Oh, no. All of these bodies. We're going to right click and make these out of silicon, I think. Okay, so the fact we've got our predetermined materials is not a problem. All we're going to do is go ahead and add some power to our model. So we've got our materials set up. We need to add a heat in, and we need heat out, and any thermal resistance, and then we're good to go. So the first thing we're going to do is, under my thermal loads, is apply a load to my LEDs. So we can either apply them as a set of temperatures, or in our case, we're going to set heat power. Okay, so when we choose different entities, if we were to choose a face, it will be generating a heat power just from this face. This would be an example if we hadn't actually modeled the bodies themselves. We might choose faces to apply our heat loads to. In our case, we have all of our bodies. So instead of choosing faces, I'm going to carefully choose each of the components. And I am going to put a per item of 0.25 watts. Okay, so it'd be half a watt each. Okay. So next we need to choose a convection. So on the same dialog box, heat in could be temperature, heat flux, heat power, and out or in can be convection or radiation. So we're going to do a convection model, and we can choose the faces that are convecting, either carefully go through all of them, or in our case we're going to choose all exposed faces. We'll populate all of those faces in my tree, and if I choose, I can deselect any particular faces that I think should not be applied, and that's close enough for me. But what we do want to do for that convection is give it a value. We're going to put a measured value that we had from previous conditions of 5 watts per meter squared Kelvin. But what's really important is that the ambient fluid or air needs to have a temperature. So we're going to set ours at about 35 degrees C or 308 Kelvin. And if you changed it to metric, you'll see it changed the units as accordingly. I'm going to hide this just for convenience, so it's nice and clear. And the last thing we're going to do is do a thermal conductivity between this aluminium plate and the PCB board, which can be done quite easily. I'm going to zoom in so we can choose those faces. And under my connections, you'll see global contact is set to bonded, which means everything will be perfectly conducting. In our case, we're going to right click and set an individual component contact, and we're going to select other, and we're going to select one face, and then we're going to right click, select other, and choose the second face. So we can specify our own thermal resistance between these. We can either have them perfectly insulated, perfectly conducting, or some thermal resistance. So in our case, we're going to have a distributed thermal resistance that's been measured. I've actually taken this value from our flow database that has many thermal conductivities for different thicknesses and materials, or you can get it from your manufacturer's sheet if you have some thermal grease or other contact information. Again, if you have thermal conductivity, it's 1 over thermal conductivity is your thermal resistance. Okay, so all that's left to do is to right click, create our mesh. with a set value. We'll just make it a little bit finer, and then we can run it. I'd be inclined to unexplode it for clarity. We can see our model, and I can run this now. I've actually run it before, but I'll run it now, see how it comes out, and then we'll review some of our results. So we can see our first plot that's come up. It's already done a plot for temperature. I'm actually going to go to the one that's been finished. And we can see on here clearly the temperature at the bottom of these LEDs pulling through to my geometry and the heat moving up to my heatsink. So what might be of interest to me is the maximum heat in each of these. So we're going to do a probe. And sometimes, like the last one, if we had a look at this thermal webinar we did, sometimes these plots can be difficult to read because of little singularities or other things. Sometimes it's important to change your scales to something you can read. Not sure what's going on with that one, but we'll come back to it later. So how do I know what the actual temperatures are? I can just read them off a chart, but rather than a chart, we would introduce something like a probe tool. So a probe tool, by right-clicking on a plot, lets us actually interrogate any individual node that we're interested in. So we can see our maximum varies somewhere between 70 and 72, 73 maybe at the maximum. And we can use that to actually extract what we're after. What might also be of interest to us is when we're right-clicking and creating plots, is entities such as our heat flux. So we can do heat flux in different directions, X, Y, and Z, or total heat flux. I'm going to do mine watts per meter squared. Let's just reduce that a little bit. So in fact I've done one before. If we keep adjusting that, we'll see that we're able to see the heat moving through my geometry up through where the chips are, and interestingly getting quite a lot of heat movement in and around this corner. Remember there was an analogy with stress that heat flux is a little bit like stress, and it doesn't like sharp corners. These plots can also be done as a vector plot that shows us the heat, actually the vector moving away from each of the LEDs and up through my geometry. We get an idea where the heat's actually going. So we can also create them in different directions. So this heat flux is for my Y, which you'll see from my geometry triad down the bottom is vertically up. So this shows the amount of heat that's moving up through my cylinders, through my fins, sorry. And this last one here, we're going to edit the definition and have a look at what it actually says. It's also Y. This is using the axis in the middle, so the axis of here. So our X, Y, and Z now become a cylindrical. So X is radial, Y is circumferential, and Z is axial. So this shows me the plot of heat leaving the fin, but moving perpendicularly out of it. So we can use that to our advantage and do some probes and other things and see how much is moving through. Okay, so taking this to the next level, we can come to our model, we can take our study and we can right click on it down at the bottom and create a duplicate of the study. So we can copy that study. We've already done that to this one large fillet, and you'll see if I activate the SolidWorks configuration, I have already changed the size of this fillet to make it larger. And we have rerun this. So when we look at our temperature plot on here, we can see that we have, if I do a probe, the the amount of heat on my LEDs has gone down from around 73 to about 68. So, about a 5% improvement, which could be quite enough to, prolong the life of your LEDs in this case. Looking at our resultant heat flux, we see we still have good heat coming up through them, but we no longer have this high concentration of movement of heat around the fillet, so it's moving more gradually into my fins. So I've created a more optimum solid geometry. So we're going to take a look at the next case study, then we're going to come back and do a transient study. But firstly, I just want to talk about, as well as talking about heat and the effects of heat on my electronics is quite important. That heat can then be used as a plot for creating a thermal expansion study. So in our case, we have a series of bellows that we're going to take a look at. If I can move where I didn't store it. One second, we'll just have to extract that 1 sec. Here we go. So I thought I preloaded it, but I must have left it behind. So here we can see, in this example, we have a full set of bellows. They're made from a stainless steel, like a lattice structure, and it has a flange on each end, so the hot gas flows through them. And so what I want to do is see how much heat goes into each of the components and see the effect of that on it. So what I've done, I've cut it in half because it's a symmetric problem. And then we've gone ahead and made a new thermal study and 2D thermal, we're going to call it. But this time, rather than me doing the whole model, we're going to save some time and we're going to use an option down the bottom of my left screen called 2D simplification. So this lets me create a slice through my model, either as like an extrusion, or in our case, we're going to have an axisymmetric. And we're going to choose an axis. And as you can see, what it does, it gives me a nice little axisymmetric slice that we can use to set my model up with. Again, the materials can come through. We've got stainless steel and plain carbon steel already defined. And all that's left to do is apply a load and a convection coefficient. So we're going to do a temperature load this time on the inside. Right click and select all my inside faces, and we're going to set these to be 220 degrees Celsius. Again, in a flow model, you would have set the gas to show the gas going through there, and you would work out how hot the surfaces would be, but this is a simplification. And I'm going to hide that. And we're going to apply a coefficient of convection for the outside. So this one we're going to do in a similar fashion. We're going to right click, select tangency. And down here we're just going to deselect this edge. And I'm going to assume that they all have the same coefficient of convection on all these exposed faces. Remember, our edges are now like exposed faces. And we can say this is at 50 watts per meter squared Kelvin. And we need an ambient temperature on the outside, which we're going to set at 308 Kelvin. I can't remember what I set it to before, but we'll leave it like that, which is fine. Okay, so we can just run that just like it is, so we get a feel for how it works, and we can see our temperature come through. Then we can go ahead and make a 2D study in the same way. But I've got one I've done before, so we'll take a look at this thermal stress. We can see on here I've added a boundary condition for symmetry on the end. In this case, I've also added, under advanced loads, for this edge I have chosen a plane for my direction. I've said it's also going to compress it 4 millimeters. But we could turn that off and remove that. And we've also put inside a pressure 0.3. Oops. So when we define a temperature load, we can take a temperature on a face by adding the temperature from another study. So we can see we can take it from the one we've just done or the one I ran earlier, and it will use that temperature to move the material. Then what we end up with is a series of thermal expansions, and also includes the displacement from my formula of movement. If I was to suppress this entity and the pressure, we will be able to run that just from my thermal expansion. And we can see about quite a bit of movement because we haven't controlled the end. So I put that in at 0. So just hold it straight on the end and rerun it. You can see just from the thermal expansion how it wants to expand and move. Okay, we're not going to do any more on this one. We're going to close this down and talk about what we haven't talked about yet, which is time. So what haven't we considered? Time. So when we're looking at how quickly does the bellows or the heat sink get that hot, we've been considering what we consider to be a steady state. So I don't care how long it takes. This is when it reaches an equilibrium, whether it would be 10 seconds or 50 years to get to that time. It's irrelevant. Time is not being considered. So in many cases, time would be important. What happens if your loads are not always on? So the heat comes on and then it comes off. Or how long does it take to get to that maximum temperature? Will it ever be in there? Maybe the ambient temperature varies from hour to hour and cycles through cycles depending on the environment it's in. Then we need to consider that as a case too. Or maybe we want to know how quickly does it cool down after we turn something off. So we can do something similar. We're going to do the heat sink again. When I make myself a new study, such as a thermal study, just like before, when I go to my properties, I can choose for it to be steady state, which is default, or transient. So I can say it could be 600 seconds and save results every 30 seconds. Okay, and I can also choose either the initial temperature starts from my thermal finished, or if you don't turn this on, you can set your initial temperature by right-clicking and adding the temperature and choosing either a Kelvin or Celsius value. Just be aware, if I choose 0 Kelvin, it will start from absolute 0 and it will be a very cold structure. It'll take a really long time to heat up. There's also a word of warning: when clicking all exposed faces, I am putting a temperature only on the faces of my solids. So the inside will still not be set at that initial temperature when I click initial temperature. Okay, so it's important not to choose exposed faces for these transient studies. In fact, best practice to do it all the time, but rather choose bodies. Likewise, when we set a load, for example, when we set, if I choose a body, I choose all of these bodies, and I put a heat power in there, because we have a transient study, we can have 0.25 watts, but we can choose a time curve and or a temperature curve. So these can vary by time or temperature. So I can say, for example, start at 0, 0, and then after 2 seconds, go to 100%. Then from 2 to 60 seconds, stay at 1. Then we could turn off. And then stay off for, we can see we can build an input graph of turning temperature on, turning temperature off. So what I've done, here's one I've done earlier. We'll take a look at this one. And we'll see this one I've also added in here, a radiation model just for interest, whereas the ambient temperature of the air is set for 35 degrees, emissivity of 0, surface to ambient. And I've set my thermal load to start at 0 until 500 seconds, when it will go up to full load, and hold until 600 seconds. And my study, I have started the temperatures from the finish. So after the steady state, we're going to see how does it cool down and then warm up again. So we can do that by taking like our temperature plots like we had before. When we define them, we can choose the step. This is at step 300 seconds, but we could go all the way up to 600 seconds. You see it's actually only at 55, so that 100 seconds it took, it hadn't reached its maximum temperature yet. More importantly, we can right click and use our probe tool, look at any of these entities, and there's a button for response, and this will show us our transient response for that single node. So on here we can see that node started at around just under 59 degrees C, and we can see it cooling off to where we started heating it again, and it's starting to heat up over 100 seconds to around 55 and hadn't reached its steady state yet. We can also take these plots and we can animate them. I'm just going to stop this. We're going to animate ours in 10 steps. And we'll see it step through the heating process. If I look underneath, it will make it more clear. cooling down, then heating up at the end. Probably doesn't show so well on the webinar, but that's fine. You can have a look in your own time. So some common pitfalls. I do have an example, but we haven't got a lot of time, so I'm not going to show it. Orthotropic materials. If you set the direction wrong, then it might try and conduct through the insulating direction quickly. The key is to look at your plots and understand where is the heat going. Look at the heat flux. Global contact set to bonded or to insulating. It's important to understand that the contact is all about conductivity or resistance. So it's important to make sure you define anything that's important, and the global contact will either be perfectly bonded or perfectly insulated. Initial temperatures for transient studies. If this is not set correctly or set to faces, if you only had faces set at one value and the rest was set at 0 Kelvin, it might take a really long time for the solids to heat up and produce really wild controls. And convection curves and transient studies can be difficult to understand. So, quick overview of solid works flow and heat transfer. So, when we set up a flow model, we create goals that are important to us. So, in heat transfer problems, typically we create goals in and around the temperature of the solids that are important to us, or the fluids, or the surfaces. Velocity of air and other things may also be important. Flow simulation solves the full Navier-Stokes equations. So just for your entertainment, I've put an example of the equations on the screen. Luckily, you don't need to solve them yourself, so you might be there a very long time. SolidWorks Flow Sim uses a laminar turbulent boundary layer model to describe flows in near wall regions, and it's based on the so-called modified wall function approach. So I actually had two studies. We're not going to set them all up. We'll just have a quick overview. We've got one for the light we're looking at, and I've got a heat exchanger for solid fuel that we've built. So in this case, keeping hold of my geometry for the outside, because we're going to create a flow model in and around the rest of it, is considered to be important. So flow simulation, making studies, is an easy, convenient wizard. It takes us through the process of what we're doing, and we give it a name. In our case, we can choose our units. I'm a fan of going to Celsius for clarity. We can do internal studies. In our case, because we're talking about external cavity, like we don't need an internal because we haven't got any boundaries. We can also include heat conduction in solids. And if we wanted to do a similar study to what we've just done, we could say heat conduction in solids only and specify our own convection models, and we run really quickly. We can also include radiation, either discrete models or discrete ordinates if you have your HVAC module. And if we want a transient study, we can turn on time dependency. Because we're dealing with convection, for natural convection, gravity is important for the air to move in the right way, so we're going to turn it on too. So as simple as that, we're going to choose our default gas or liquid. We have choices to choose more than one. We only need one for ours. And we're going to choose our default material as copper. And we're going to work with our defaults all the way through. I'm not going to look at the details for this seminar. It's really about heat transfer. Okay, so we have our first study, and actually you'll see, here's my computational domain. I can click on this and I can alter it and tweak it. Oops. By dragging these arrows and making it a little bit lighter for solving. Okay. Solid materials, again, we can apply them in the same fashion, but more often what we'd like to do is utilize some of the SolidWorks tools, such as searching for all ABS in my model. Using the filter key, I can do that. I can select all my geometry, it's pre-selected. Right click, insert a solid material, such as one from my previous model. Likewise, if I want to find anything that's got power function in there, we can see, especially if I turn off my cross section, we can see all of these can be done and selected and added in one hit. Before I go too far though, I did have one example I was going to show you. And this example is a wee circuit board. So setting up all my materials and all of my circuit boards can be quite an onerous process when I have many components. Such as in this case. In fact, if we look at any one of these components, you'll notice that the properties for this have already been added to the geometry for specific heat, thermal conductivity, and the power output. So this metadata could have come from Altium, from your PCB designer. Maybe it could have come from a manager or somebody that has put it in your PDM system. It's all been propagated into the SolidWorks files through your management system, your data management system. So now we have it in there, we can actually utilize that to create those models quickly. So in here, for example, if I want to right click and insert my solid models, I can actually import them from my model. So it's imported, and you'll see the list here is quite extensive. All the volumetric heat sources and materials and any other data can be added and imported in one click. Also can import my goals as well as materials all in one hit. So we can see in my model, now we've done a setup, all of these materials have been added, all 136 plus another 20, so about 150 materials plus 186 volumetric heat rates. Okay, so we can utilize some of the SolidWorks tools to very quickly and easily set up our geometry and be consistent so that right people are making the right choices about what's in there and what's not. In our case, I'm going to go to one that's been set up before. In this case, you'll see these, instead of using just a heat source, these have utilized what's called a 2-resistor component. It gives a more accurate transfer using the junction and the case. So this is part of the electronics cooling module. I just left it on there just for an example. These have all been pre-added. Adding goals, we can insert goals on any type of geometry. So typically for an electronic component, we're interested in the volumetric heat. How hot does the volume get? So I can look in here, for example, down under temperature and choose my geometries. For example, these two, I could say, please make a goal for these temperatures. And these volumetric goals can be done while we plot it. Okay, so this has been run already. To save time, we're going to load those results. And we're going to take a quick look at the goal plots for one of these LEDs. So we can see my study has run run one of these LEDs, we can see the temperature converging on a steady state of around 90 degrees Celsius for one of my LEDs. And we can hide that plot. We can do quite a lot. We've added in here some cut plots. We're going to show one first. This one shows the convection model quite clearly. It's showing temperature in my model, and this can be slid down. Shows clearly the heat coming out through my heat sinks and creating this convection column up through here. We can use a probe tool in a similar fashion to actually probe the heat of my air in my model and on each of my entities. Okay. We can change this temperature to be a velocity plot and continue to probe, and these probes stay on screen, giving us great abilities to create rich content. Okay, and we can tweak and change these models to be however we want them to be. In this case, maybe what we would do would even be add streamlines to it. Let's hide that one. We're going to look at one more. Just down through here, we can see there's one for, I'm going to put it onto temperature. And we can see the temperature in my model coming through. So in a flow model like this, what we can go ahead and do is choose to do plots such as, I'm going to do one for the flow trajectories. This will actually show the heat moving through my structure, and that could be animated very simply. And doing our ISO surfaces, allow me to actually show me areas of equal temperature in this case, so I can see if I was interested in everything that was above, say, 50 degrees C, we create a plot of that. These are the surfaces at 50 degrees C or above, and see how close we're getting. And quite interestingly, how we're creating this bubble inside of here because the vents aren't there. Maybe it'd be better to have material and force the air out of the holes. We're not going to do any more on that. The one thing I do want to talk about is in this design, how do I work out how many fins? So in flow simulation, we can do what-if studies quite easily. In this case, I've taken the value of the circular pattern, 20, 40, 60, 80, and 100, and got it to run each of those studies based upon a goal that I'm interested in. We can see we've got 5 outputs, and we can see that the temperature of each of those LEDs that we looked at changes from 91, and then at 40 fins goes down to 80, 88, and then it starts going back up to 89, 90, 92. So we can see it somewhere between 20 and 60 is an optimum number of fins, whereas if we got too many, we stop getting airflow through those fins, and the temperature is unable to dissipate as clearly. Lastly, we're going to take a quick look at the heat exchanger model, just out of interest, so we can see how this can be applied to more complicated structures. In this case, we can see inside of here we have, I'll take a look at one of these, so it'll be good. We have an inlet manifold that lets air come through. We have a cylinder representing our solid fuel, and we have some holes to allow the air to come in. So we have set a static pressure on the inlet face, allows air just to come in on its own accord, and we've put an outlet fan to pull the air out of the way. And I've put a heat source at 15 kilowatts on my cylinder, and we've set some goals to monitor. So we're going to load the results on this, and we can see it will give us quite a lot of insight to the model. So as the air gets pulled from the heat source and the fan, we can see the air gets pulled, and because of this hole here, it's actually getting pulled quite quickly in through the large hole. And actually, we'd probably like to get a big flame kicking out the front if this is what we wanted, or maybe we'd want to move the inlet position to try and dissipate the heat more evenly. And the air's coming up through the top, down through the sides, into the ash box and out the back. I'd love to show a little bit more, but we'll have to save that for another day. Some of the further topics for flow simulation: we can do supersonic flows, we can do adaptive meshing, so the mesh changes as it solves, we can mix fluids, we can do cavitation, including non-Newtonian fluids such as oil and blood, rotating machinery, particle studies, optimization, humidity, electronics, cooling, and HVAC conditions. So a little quick summary of our event from today. Talked a little bit about why we should use simulation, had an introduction to the types of heat transfer, some examples of doing a heat LED light in Simulation Professional. Talked about how we can use those thermal results not only for temperature plots and conductivities, we can also do it for thermal expansion. We introduced steady state transient studies, and a little bit some of the common pitfalls in Sim Professional. Introduced flow simulation and had a look at the same LED and a heat exchanger quickly, and discussed some of the other types of studies we might have in flow.